All right, welcome Ralph and Cesar and Bradley and Jordan and Jesus and whoever else comes on in. This is yet another webinar, and we're kind of continuing on. Again, we're still in this 4.10, which seems like the section that never ends, but we're actually finishing it today, and we're actually going to do a little of the next section too, tiny of the next section. But the section we're in now, that's the big section for the whole course. And that's why we're spending so much time on it. There's a lot of material in this one section, so don't take it lightly. So let me share my desktop and talk about the plan for today. Okay, so the plan today is I'll start out with Q&A, whatever questions you might have. That could be about homework or other things, or the exam or whatever. And then after that, we're going to get into matrices. What a surprise. And in particular, we can look at the row space and the column space of a matrix. So a big part of what we're doing today, at least the end of the 4.10, is we're going to be looking at a matrix and saying, well, thinking about the matrix as vectors, now let's talk about all the things we dealt with in vectors. And one is, what is the row space and what is the column space? Another is, what is the rank of a matrix? And again, these are definitions, and we'll get there. There'll be a theorem about the rank. And then we've already talked about the null space really fast. That was a while back. I think that was Friday. But I'm going to review the null space and then also talk about the image of a matrix. So as I've mentioned a few times, matrices are functions. So that's why you think of an image. In other words, what is the range of the function that is the matrix? And we'll take a look at that. And what is the null space, which we've already talked about. And then we'll talk about theorems about rank and nullity of a matrix. And then we'll be finished with 4.10. So again, we're spending a lot of time on 4.10 because it is the most important section, I think, of the whole course. So, don't take that one lightly. That's why we're spending so many days on it. But we're going to move on, and we're going to move on to 4.11. And 4.11 is important too. Nothing like 4.10, but it is, there's some important things involved. And we're just going to do a little bit of 4.11. We'll do, I think, the rest of 4.11 on Friday. And the parts of 4.11 we're going to do is we're going to say, what does it mean for a set of vectors to be orthogonal? Okay. And then we'll say, what does it mean for a set of vectors to be orthonormal? And then we'll say, if you have a matrix, what does it mean for the matrix to be orthogonal? And it turns out this number 9, what an orthogonal matrix is, very misleading. So I'm going to give you a warning on this one. This is the easiest one to get confused about, because I think, and don't get mad at me, I'm not the one that made the definitions of all these words, but if I had my say in things, we would not be calling it an orthogonal matrix. But I need to talk about what all the mathematicians are doing. So I don't know why that was happened, and what you'll see, I think you'll believe me too, that was a poor choice of words, but we'll define that. And that'll be the plan. And I want to give you a reminder, and that is a week from today. What's happening?
Exam 1.
Exam 1. Okay, so it's time to start thinking about it. The exam 1 will cover everything from the first day of class, and then all the way up until what I talk about on Friday. So we're not quite ready to go talk about all the concepts of exam 1 because we don't know Friday stuff yet. But then Monday we'll have a nice review for exam 1. So that is the plan. So now I'll ask questions, and I can see there's one already, and that is problem 46. So let me go find it. So it'll take a second to get 46.
Are you excited that it finally snowed?
Oh, it's beautiful. Shoveled today. The skiing's good. I mean, it has snowed, but it's really good snow now. And then, what happened? Just 1 second. And copy. And paste. Okay, so here's 46. Okay, so what it says is let M be the set. Okay, I tend not to use the letter M, but the book does. Just let you know, I tend to use S for set. I like M for matrix, but you have to live with the book. Okay, so let M be the set of all U, such where U is U1, U2, U3, U4 in R4, such that U3 equals U1 equals 0. Is M a subspace? And we need to explain why or why not, which is basically saying prove it. Okay, it's a good question. How many different things do I have to look at to decide if something is a subspace or not?
You need to know if it goes to the origin.
So how many different things?
3.
3. Okay, so I want to remind you that to show something's a subspace, you need to show 3 things. To show something's not a subspace, if you only show 1 is wrong and then you're done. But we'll see on this one. Okay, so what's the first thing I have to show? I have to show it goes to the origin. And I don't like to use the word origin. I like to say it contains a 0 vector. And the reason I'm going to say that is, even though it feels like the same thing, when we move on, when we get into the second half of this class, and vectors become not just a bunch of numbers, all of a sudden origin doesn't work. So the question is the 0 vector, and let's write this down. I'll write number 1, and that is 0, and that is the 0 vector in M. Well, is it?
Yes.
Yes, because the 0 vector, and I'm not going to write in column. Column takes too long to type. Are you okay with rows? 0, 0, 0, 0. I know it's not exactly what they're writing, but are you okay with that? It just saves a lot of time in terms of typing. So notice that has U3 equal U1 equal 0. Do y'all agree?
Yes.
Yes.
Okay, so good. I'll just write good. It means we got it. So number one so far, we have not violated being a subspace. Is that clear? Okay, number 2. What's number 2?
And it needs to be closed under vector addition.
Good. So let's take a look. Well, let me give you a general vector, and I'm not going to use 1s, 2s, and 3s anymore. I'm going to, because it's just messier. I'm just use A's, B's, and C's and stuff. So something in M, we need U1 to be 0. So we're going to start with a 0. U2 could be anything. Let's call it A. U3 has to be 0. And U4 can be anything. Let's call it B. Any questions on that as a general example of a vector in M? Okay, and then I'm supposed to add it to another vector in M. And in general, that's 0, comma, let's call it C, comma, 0, comma, D. Any questions so far? Okay, and by the way, in this class of math is really never hard. What's hard is knowing what to do. So I hope you all can do this addition. What do you get? First component is?
0.
Second?
A plus C.
A plus C. Third is?
Also 0.
Yeah, 0 plus 0. You all be able to better do that, by the way. And then the fourth component?
B plus D.
B plus D. So now the question is, does that have U3 equals U1 equals 0?
Yes.
Yes.
Yes. So that's good. I'll just write good. Any questions on number 2? Have I done anything tricky?
No.
No, this is literally following the definition and just checking one step at a time. Takes a while because we got 3 steps. And let's get to our 3rd step. And what is the 3rd step all about?
Must be closed under scalar multiplication.
Good. So I'm going to call K my scalar. And then I'm going to have 0, comma A, comma 0, comma B. That's a general vector. Except it made it capital. There we go. And let's do that multiplication. This is supposed to be easy. What happens when you multiply a vector by a constant?
Multiply each component by the constant.
Okay, good. And K times 0 is 0. K times A is KA. K times 0 again is 0. And K times B is KB. Any questions on that idea? Okay, does that have U3 equals U1 equals 0?
Absolutely.
So that's good. So what's the conclusion?
M is a subspace.
Yeah, so therefore, M is a subspace of R4. By the way, is M a subspace of R5? 1, 2, and 3 work.
No,
Why not?
because we need one more component.
Exactly, exactly. It's not in R5. So the first thing is it has to be a subset. So I didn't mention that with this example, but hopefully it's obvious this is a subset of R4. Okay. But if it asked about R5, the answer would be no. Because it's not even in it. If you're not even in it, you have no chance. Any questions on that? Any questions that make total sense?
Yes, absolutely. Thank you.
Easy to watch, right?
That's true. Yeah.
Yeah. But I want to let you know, there's a good chance I'll be asking you a question like this. It won't be this question. And yeah, you need to show 1, 2, and 3. Okay. Or find 1, 2, or 3 that doesn't work and say that it's not a subspace. And that's how these work. Okay. Other questions? It was a good question, an important one. 47. I see
If
47.
one of these components is a linear combination of the other, it can't be on R4 neither, right?
One more time. If
one of the well, I don't think it belongs to this case, but if we have something similar, a matrix, and we have a row that is a linear combination of others, that means we are not on R4.
So being in R4 just means you have 4 numbers. That's all that means.
Okay, but to be a subspace of R4,
To be a subspace, you need 1, 2, and 3. To be a subspace, you need 1, 2, and 3. So you just got to check 1, 2, and 3. Does that make sense?
Yeah.
So if you have 1, 2, and 3, then and it's in it, then it's a subspace. If any of 1, 2, or 3 is false, it's not a subspace, period. Okay, or if it's not even a subset, you have no chance. And that's it. I mean, really, that's the rule on this one. Does that make sense? We will have more theorems about when something is a subspace, but they're more abstract, and we're not there yet. Other questions on this? Okay, let me find 47. So let me grab it. The nice thing is it's right after 46, so it's easy to find. Okay, so here's 47. So consider the set of vectors given by S equals the collection 4u plus v minus 5w, 12u plus 6v minus 6w, 4u plus 4v plus 4w for u, v, and w in real numbers. Is that a subspace? Okay, and same question, explain. Oh, we're supposed to find the dimension. We're supposed to find the dimension of the last one? No. Okay, so this one, if it is, we have to find the dimension. All right, so, well, hopefully you know that we need to, first thing, notice that there are 3 components, so it is a subset. So you need that first. But now we need to do 1, 2, and 3. Okay, so what we need to do is we need to say, are there numbers u, v, and w that give you the 0 vector? What do you think? This is a really easy, dumb question. Yeah, what number?
Yes.
Yeah,
0.
which numbers? Yeah, 0, 0, and 0. So let u equal v equal w equal 0, then you get the 0 vector, or we get the 0 vector from the definition of S. I like S better than M. Good. And therefore, good. Are you okay with that? Okay, so the next thing we got to do is we need to do addition, right? So this one's going to get a little bit messier. I'm going to keep it with, I'm going to make it horizontal instead of vertical. Hope that's okay with y'all. Technically it's vertical, but that really doesn't make a difference. But we need to say, let's suppose we need to choose a general u, v, and w. So how about a, b, and c? So we're going to have 4a plus b minus 5c, comma, 12a plus 6b minus 6c, comma, and then we're going to have 4 of each, 4a plus 4b plus 4c. So that's our first vector. Do y'all agree that's a general vector in the set S?
Yes.
Okay, now I have to add it with another general vector. I think the easiest is copy and paste and change the letters. So instead of A, B, C, I'm going to get very boring. How about D, E, F? So hopefully you're like me and look at this as busy work. That there's not much going on here. Are you feeling that? Because all we're doing is we're adding. All right, now more busy work. Equals. So now I got to add the vectors. And is it okay if I do the algebra as I add? So if I add the first components, I get 4 times a plus d. Plus b plus e. And then minus 5 times c plus f. Any questions on the first component of this vector? Okay, now for the second component, I'm going to get 12 times a plus d. Because it's 12a plus 12d. And then we're going to have 6 times b plus d. And then minus 6 times c plus f. Comma. Any questions on the second component? Okay, so hopefully you agree this is busy work. Does it feel like it? Okay, then we're going to have a 4 times A plus D. And then plus 4 times B plus E. And then plus 4 times C plus F. And that's the third component. Any questions on getting the sum of two general vectors? Okay, now is this of the right form? So is this of 4 times something plus something minus 5 times something, comma, 12 times something plus 6 times something minus 6 times something, comma, 4 times something plus 4 times something plus 4 times something? Do we have the right form?
Yes.
Yes. So notice is the right, I'm going to write is of the, I'm going to call it S form. So good. Any questions on number 2? Okay, so we've done number 2. Now we go to number 3. So 3 says we take K times some general vector, and I'll just do A, B, and C again. And I can pop that guy in, so I don't have to type it again. So it's K times the general vector with A, B, C. And then we do what we expect. We multiply K through. So there's very little to do here. I mean, it's just it's messy, but it's not, I don't think it should hurt your head. So I multiply the K through and I get 4K A. Let's see, how do I want to write this? Yeah, that's fine. Plus KB minus 5KC. And then 12KA plus 6KB minus 6KC. I'm just multiplying the K through. And then 4KA plus 4KB plus 4KC. So is this of the right form?
Yes.
Yeah. So now our letters are KA, KB, and KC, and those are all real numbers. So is of the S form. So good. Okay, we're not done yet. How come? We have 2 more things to do.
Find the basis and
Yeah.
mention.
Before we find the basis, we need to actually, because a lot of people forget this. You need to say, yes, it worked. Does that make sense? So therefore, S is a subspace. Of R3. I'll just write subspace because that's what it asked for. Any questions so far? Okay, so now we need to find the basis. And I'm going to tell you something that I don't think it's in the book. I don't think I've mentioned yet, but it's really helpful. And that is when you have something like this, what we can do is we can take a basis for R3 because we're talking UVW. And U comma V comma W represents R3. And we can use that basis to get a basis for S, or at least try. It may not give you a basis, but it'll at least give you vectors that you want. So in particular, what is the easiest basis in R3? Even had a word.
Identity.
Identity wasn't quite the word. Yeah, you probably had the right idea in your head, but we called it something. Remember? It's called the standard basis. Do you remember that? So we're going to use the standard to generate U, V, and W. So what we do is let's use the first one. That means U is 1, V and W are both 0. And what you get when you do that, you get 4, 12, 4. Any questions on how I got that? Okay, then what we're going to do is we're going to use the second element, E2, which is 0, 1, 0. So that means U and W are 0 and V is 1, and we get 1, 6, 4. And then I'm going to let U and V be 0. W is not 0. So W should be 1. And we get -5, -6, 4. Any questions on that? Okay. And that will give you, at least a spanning set for S. Do you all agree?
Yeah.
Because remember, S is, this is defined this way for general U, V, and W, but general U, comma, V, comma, W can be written as a linear combination of E1, comma, E2, comma, E3. And that's what I just did. So if I do it for E1, E2, E3, I've got them all. So now we're going to take this. So we know that the span, so we know S is equal to the span of this set. Is that clear? Totally clear?
Yeah.
All right. Well, hopefully you know. How do you find the span of a set? What's the easiest way?
Put it in a matrix and RREF it.
Yeah, and I recommend doing it on a computer. Did anyone do that?
Yeah, I have it.
Okay. And that'll take me a moment because first thing I need to bring it down so that we can get on a page. This is a long one, so may not even fit on a whole page. Okay, so we need to get the matrix. Let me make matrix form. I forget to hit backspace first. There we go. So let's go matrix form. Okay, what's the first row?
1, 0, -2.
What's the second row?
0, 1, 3.
And what's the third row?
All zeros.
And I need to ask you, because it's actually really important. Did you use the matrix where 4, 12, 4 was a column or a row?
Column.
Okay, so that's important. So notice that if that is the column matrix, then if we want to find out a basis, we can say that the first and second columns are pivot columns. Got it? Can you see that from the answer here?
Yeah.
So since the first and second columns are pivot columns, that means that the first and second vectors, original vectors, 4, 12, 4, and 1, 6, 4 is a basis for S. Any questions on that? Any questions? That was a lot of work, but it worked. Oh, one more thing. What's its dimension? That should be easy.
2.
Yeah, therefore, the dimension of S is equal to 2. Because there are 2 vectors in a basis, and that means 2. Does that make total sense?
Yeah.
Okay. All right. Just a note, because we're doing this today, you're not expected to know how to do this yet, but you will be expected in another hour and 15 minutes. And that is that S turns out to be the image of the matrix 4, 12, 4, 1, 6, 4, -5, -6, 4. Okay, so we'll get into the definition of image of a matrix, but that's what S is. And then we'll have all kinds of theorems about how you find the image, and we'll realize the image is always a subspace. So there'll be a theorem that says, yes, S is definitely a subspace by theorem, but we don't have that theorem yet. So this is one of those you got to trust me, that there's going to be there's going to be a nicer way of doing this one, because this one comes up so often, it's better to just have a theorem about it. Okay, any questions on this problem? Okay, if not, I think I'm going to move to new material, because I don't like to spend too much more than a half an hour on questions. Hopefully that's okay. And I want to remind you, I always have office hours after. And the good news is, which you know, unless you're like, I don't know, you're just like on weird drugs or something, that I have internet access. So we actually are having this. I was a little worried when I saw the weather report, and then I got an email from a friend saying in Tahoe saying that hers is down. So I was like, oh man, I hope ours doesn't go down. So the good news is we're good, but if something happens, then you'll know what happened. So if all of a sudden I turn off, then my internet died. But it looks pretty good. It's not even snowing hard right now. All right, so now comes a big definition. Okay, and I know I say that every time I give a definition, but these are biggies. They're not quite as big as linear independence and span and basis. Those are the three biggest probably of the entire course, but these are important too. And that is the column space of a matrix A is the span of the columns of A. And the row space of a matrix A is the span of the rows of A. Any questions on this definition, what it means?
So for that last problem we just did, when you asked me if I had it lined up as column or rows, you were kind of hinting at this right here, yeah?
Also, there's another thing I was talking about. If you happen to have it as rows, which I'm about to do, then you actually don't have to go back to the original S. You can just use the rows themselves. But that doesn't work for columns.
Okay.
And we'll get into that today. That's why I asked, because I wanted to see, can I sneak something in today? And the answer is not yet, because you had them as columns. So it turns out, even though the book doesn't do it at the beginning, it's better to write them as rows than as columns. If you have a choice on how to write your vectors, rows are better than columns. Okay, and there's a reason that's coming right now. Does that make some sense? So there was a reason why I asked, but it wasn't something that you would understand why I asked until now. Okay, so let's do an example, and they're not hard. Actually, before I do the example, I want to give you a lemma so I can do the example the easy way. And here's a lemma. Do you guys remember what lemma means? And it's not some citrus fruit, by the way. Remember what lemma means?
Doesn't it mean like rule or something? Or is that a corollary?
Okay, corollary is kind of in a way, the opposite of lemma.
Oh.
So lemma is a precursor to a big theorem. And corollary is a result of a big theorem. So lemma comes before, corollary comes after. Does that make sense? So lemma is a theorem, but it usually means that the purpose of it is to prove another theorem. Okay, and here it says, elementary row operations do not change the row space of A. Therefore, A and RREF of A have the same row space. And the rank of A is equal to the dimension of the row space of A. Okay, so it's an important lemma. So we want to get into this lemma and let's prove it. It's not a hard proof. That's why I think it's worth proving. All right, so to prove that elementary row operations do not change the row space of A, there are three things we have to show. What three things? And they're different than the three things we just did. Completely different. This is something you have to remember or you won't do well on the test next week.
The row operations effect on the determinant.
Actually, nothing to do with the determinant. Nothing to do with determinant. But here, the key is the number 3. That number should like ring a bell about what we're talking about.
It's closed by scalar multiplication.
That's one of them. 2 more.
The zero vector it contains the zero vector.
No. This is not about subspaces.
Okay.
This is about elementary row operations.
Oh, you can swap rows.
There we go. If you swap rows, then you don't change the row space. What else could happen?
You can multiply by a constant.
Right, and that's that constant that I kind of agree with you. Yeah, you can multiply by a constant. You can replace a row with it plus a constant times another row. So to prove this, we have to do 3 things, right? We have to show that each of the 3 elementary row operations don't change the row space. Is that clear? So 1. Well, switching rows. All right. Well, is that going to, if you change the order at which you look at the vectors, does that change the span of them?
No.
No.
No, the order has nothing to do with the span. So the order that you list the vectors has nothing to do with the span. So that means switching rows does not change the row space. Because remember, the row space is the span of the rows. And switching just changes the order at which you read the rows. Is that clear? There's nothing to do there. Okay, how about multiplying a row by a non-zero constant? So the idea is that if, and I think I'll make it pretty. V1, comma, V2, comma, VK. Actually, it's not K anymore. Now it's M. Because we're talking row space, and there's M rows in a standard matrix, right? That's what M always stands for in this class. So if V1 through Vm are the rows, and I'm going to do a W log. Remember what W log means?
Is without loss of something?
Yeah, without loss of generality. So we're going to multiply the first row. By a non-zero constant. To get k times v1, comma v2, comma dot dot dot, comma vm. Is that clear so far?
Yeah.
Okay. And again, had it been the 8th row, we'll just switch the 8th row and the first row, and now you're doing it for the first row. So that's why I can really do that. Okay, we can just say it's the first row because it doesn't really matter. Well, now the question is, do these two sets have the same span? In fact, I think I don't want to use those brackets. I think I want to use these guys because these are sets. Do they have the same span? Let me give them letters. First one is R, not even letters, but I'm going to actually write down what they are. Row space of A equals that. And here, it's going to be the row space. Whoa. One more time. Of, instead of A, I'm going to call that E2A. Because remember, an elementary row operation means you're multiplying by the E2 in this case. Okay, E2 being the second row operation, multiplying by K. So are they the same? Take a look. If you look at the span of those two, that's the row space means that. So let's put span. Do they have the same span?
Yeah, they would.
Yeah, because notice that the span of A, so the first is by definition the set of C1, V1 plus C2, V2 plus dot 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 C M VM. And the second is, well, it's the same idea. Except instead of the C1, you get KC1. But KC1 is still just a constant. Any questions on that? So they have the same span. Any questions on that? Okay, for number 3. So I think it's worth it to do a proof. Okay, for number 3, I'm going to do a W log. So let it be row 1 and row 2. And again, if it's not row 1 and row 2, you can always do the first row operation, switch it. That's not changing anything until you get to row 1 and row 2. So in that case, we're going to be looking at, again, the row space of A, which is a span of V1, V2, dot, dot, dot. And then we're going to have, let me copy this and paste and change it. The row space of E3A, which is a span. Now it's going to be it's going to be V1, comma, KV1. Oops, missed. Here. KV1 plus VD2, comma, dot, dot, dot. That's what the new matrix has its second row. The first row plus the second row plus K times the first row. Anyone lost on that? All right, but that's the good news. So now we could go ahead and I'm going to copy this and look at the span. And now instead of KC1, V1, you're going to have KC1. You're going to have, C1, V1 plus, and then you're going to have, now it's going to be KV1 plus V2 times C2. So that's going to be plus KC2 V1 plus C2 V2, and then plus dot, 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 dot. Any questions on that? Well, then I could do a little basic algebra. And I could factor out the V1. And when I do that, I get C1 plus KC2 V1 plus C2 V2 plus dot, 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 plus CM VM. I've got the pluses there. Any questions on that? But C1 plus KC2 is a constant. Do y'all agree? And then I'm done. Because it's exactly the same as what we started with, which was this guy. So this one and this one are the same because C1 plus KC2 is just another constant. I think I have my K in the wrong place. It's actually KC1 plus KC2 plus K plus C2. There we go. Is that right? Oh, no, I had it right. So that's the proof. Any questions on that? Okay, by the way, why is that enough to show RREF of A will have the same row space?
Because we didn't change anything about the rows.
Yeah, but it's something about RREFing.
It's unique.
It is unique, but that's not what it's about. It's about how you RREF. Remember? So let me write it out. So since RREF of A can always be written as E1 times E2 times dot, 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 EK. In other words, do a bunch of elementary row operations times A. So you RREF by doing an elementary row operation one at a time. And if each time you don't make any changes and you do it a whole bunch of times, you haven't made any changes. Is that clear? So therefore, A and RREF of A have the same row space. Any questions on that? Okay, and we can also say that the rank of A is the dimension of the row space of A, because the dimension of the row space of A is the same as the dimension of RREF of A, which is the rank of A. Okay, so that's immediate. Any questions on this lemma? It's a big one. It's an important one. We'll be using it all the time. We'll do it without even stating it. It'll just be, yeah, we can do that. Okay, so let's move on. And this is a big note. Everything I've been doing has been about row space. Now in the definition, I said there's a row space and a column space. So the nice thing is that if you want the column space, just take the transpose first, find the row space, and then retake the transpose. And now you have the column space. So we take a transpose to get the associated lemma for the column space. So this proof works. You just have to take the transpose first. Any questions on that? So RREF of A transpose has the same column space. Sorry, the transpose of RREF of A transpose has the same column space. Any questions on that? So if you want to find the column space of a matrix, take the transpose of the matrix, RREF it, look at get the row space of that, and then take the transpose of that row space, and that's the column space. Okay, so here's an example. Very easy, or generally easy. Find the row and column space for this matrix. So what do? What's the easiest way of doing this one?
Swap row 1 and 2.
Easier than that.
Oh, use a computer.
Yeah, absolutely. And what are we going to use the computer to do?
RREF.
Yeah. So we're going to RREF this in a computer. I'm going to give you a moment. We have some time, a couple minutes to see if you can RREF this in a computer. So open up a new tab and then Symbolab or whatever you use and RREF this and see what you get. In fact, I'm going to, what I didn't do and I probably should, I'm going to call it A just so I can, makes it a little nicer. So now I can say RREF of A is equal to, and this will take you a moment, and then I'm going to have you read it to me or put it in the chat box. So it won't be this. Maybe I'll even pop these out while you're working them out. And we'll get those numbers in. Okay, 104 for the first row. And then 0, 1, -9. And then you should have 2 rows of zeros, which I know because I actually made this question to make it interesting. Okay, so here's an easy question. What is a span? So the row space of A is the span of what set? And the answer is it's very easy.
V1 and V2.
Yeah, but even easier, 104 and 0, 1, -9. So you can't just say it's 2, 1, -1 and 104. That may work, but it doesn't always work. There's no guarantee. Because remember that you get to switch rows when you're doing elementary row ops, but you can always use the RREF and say that that's in there. Comma 0, 1, -9.
So with doing it as a row space, the RREF form are the vectors we use.
Is the easiest, yeah.
Okay.
Okay, if you need to use rows of A as your basis, or then what you do is you take the transpose of A first, and that will work. Does that make sense? And then look at the columns. Okay, the column space is equal to the span of what? And I'm going to write these horizontally, even though probably technically you should write them vertically. And the key is you can't just write 1, 0, 0, 0, 0, 1, 0, 0. That doesn't work. But what you can do is you can write 2, 1, 3, 5, comma 1, 0, 2, 2. Maybe I'll even put transpose so that I can emphasize the fact that these are columns and not rows. Any questions on that? Was that easy?
Yeah.
Yeah. Not a big deal. Okay. So here is, oops, wrong one. Here's a big theorem. Not the biggest theorem, but an important one. And this is one is the dimensions of the row space, the column space, and the rank are all equal. Number 2 is the rank of A equals the rank of A transpose. Number 3 is the rank of A is less than or equal to the minimum of M comma N, where A is an M by N matrix. So if I ever use M and N, that's what I mean. Doesn't like my spelling. I'm ignoring you. Oh, it really doesn't like it. And number 3 is that if B and C are invertible, then the rank of A equals the rank of BA, which is also equal to the rank of AC, where B and C are like matrices that you actually can multiply. So the dimensions have to be right. Any questions on this theorem? Okay, why is it true? Let's look at number 1. Why is number 1 true? So we've really proved this already. A long time ago. Not years ago, but days ago. Actually, weeks, I think.
Taking the transpose of a matrix doesn't change the uniqueness of the RREF.
That's number 2, right? How about number 1? So it's not about uniqueness, it's the rank. And it had to do with how do you find the rank of a matrix? We talked about that already. Not today, but another time. How do you find the rank of a matrix?
You RREF it and count how many pivots you have.
Good. Okay. How do you find the row space?
RREF.
You RREF it. And if you want the dimension, it's the number of pivots. How about the column space? Same thing, right? You RREF, the number of pivots is the dimension. So the way you find the dimension is exactly the same for all 3 of these. Is that clear? So that's the proof of number 1. This is one of these I'm going to prove by saying it. Number 2, rank of A equals rank of A transpose. Same idea because the row space of A is the column space of A transpose. Because remember, transpose switches rows and columns. It does nothing else. Okay, why is 3 obvious?
Because the rank can't be higher than M or N.
Yeah, because because you can't have more pivots than rows, and you can't have more pivots than columns. Because each time you get to the next pivot, you go down and across. And you run out of space to go down and across if you go too big. Okay. And number 4, where does number 4 come from? We've actually proven this one already too. So think about invertible matrices. How can you write an invertible matrix? Remember? It means you can write it as a product of elementary matrices times the identity. And the identity does nothing to a matrix, and the elementary operations do nothing to the rank because we just proved that in the lemma. Any questions on this theorem? So I said the proof of this theorem instead of wrote it down because I can only write so much and then we run out of time. Any questions at all on this? Okay. Now comes the biggest theorem of the quarter, which is?
TFAE.
Exactly. And guess what? I have a new one. So here's the new TFE. TFE, I don't know if you remember, but before we had 7 of them. And now we have 8 because we're adding one more. So A is invertible, RREF of A is the identity, determinant of A is non-zero, columns are linear independent, the rows are linear independent, the columns of A span Rn, the rows of A span Rn. That's what we had before. And now we could say the rank of A equals N. So why does that work? Because we didn't have the rank of A equals N before. Now we have it.
Does n equal the number of rows?
Yeah. So whenever I say there's a matrix, the square matrix or an invertible matrix, the n always represents the number of rows, which is the same as the number of columns. Yeah, it's the amount of pivots, right? So the rows of A span Rn. That means that RREF of A must also span Rn. Well, if you have a row of zeros, you don't span Rn. The only way to span Rn is RREF is the identity, which means the rank must have been n because then you have n pivots. And that's the newest proof of this number 8 on TFAE. Okay, and I want to warn you, we're only in week 4. And this TFAE doesn't stop. Okay, it's going to get longer and longer and longer. And the way I do TFAE when I go from lecture to lecture is I just copy and paste and then add another one in, or a couple of them in this case was just one. Any questions on TFE? Okay, if there's no questions on TFE, let's do more definitions. So we're in these matrices now. So if we have a matrix, then we've already talked about number 1, but I want to kind of put number 1 in the group it belongs in. So the first is just a review. The null space of A, also called the kernel of A, is the set of all vectors V such that AV equals 0. Okay? It's kind of like the roots. You know, it's what you plug in and you get 0. It's like saying a root, except we use null space or kernel for a matrix. And that we had last time, I believe, maybe. But now we have it again. And the reason why I want to have it again, because I need to talk about the next one. You can't talk about the nullity without talking about the null space. The nullity of A is the dimension of the null space of A. So that's a new word. Not a whole lot of new concepts there, but it's a word. Nullity is the dimension of the null space. And then the image of A is the set of all vectors A times V for all vectors V. Any questions on that so far? Okay, Why do you think we call it image?
Perhaps the geometry of it.
Yeah, it's geometry, and in particular, A is a function. And the image is the same as the range. Do you all agree? And the range is, if you think of like f as a function, the range is all of f of x for all x. Do you agree? Where the domain are all the x's you can plug in, and the range is all the f of x's. Is that clear?
Yeah.
So if you want the range of a matrix, well, instead of f of x, we don't use the letter f, we use the letter a. And we don't use of, we use times. Okay, but the reason why we define multiplication in such a weird way instead of the natural way is we want it to work as a function. Any questions on that? So let's do an example just for fun. So I'm going to type again. Let's use this one. Okay, so here's an example. And I have two questions for you. The first question is, what is the kernel of A subset of? So R what? Is it R10? Is it R1? What is it?
In this case, it should be R4.
Okay. Why do you think so?
Well, now I'm not sure because I was looking at it as column vectors instead of rows.
Yeah, here's our A. I've just given you this A. Got it? And if you tried to multiply it by a an R4, let me get one. What would happen?
You wouldn't happen.
It wouldn't happen. So one thing is the null space cannot be in R4. What's it in?
R3.
Good. So the null space is in R3, not R4. Let's write this down. So for this A, the null space of A is in R3. Okay, because if you can't do that, then you have no chance of finding the null space. You got to at least know what universe you're looking in. And if you don't know the universe, you have no chance. Do you agree? Okay. How about the image? What's the image in?
R3 as well.
Okay, well, let's try something just for fun. What do you get when you multiply those? Do you get something in R3? So multiply A times this vector. And what are we in?
Will be in R4.
Yeah, we'll be in R4 because you take a dot product 4 different times, right? One for each row. So it's going to be in R4. Here, 4. Any questions on that? Okay, so in general, if A is an M by N matrix, the null space of A is in R what?
RM.
RM, good. And the image of A is in R
And
N. Okay, any questions on that? Okay, so that's just noted. Like I said, if you can't get that down, then you really don't understand the null space in the image, because those are pretty simple ideas. Finding the null space and finding the image, that one takes more work. But if you understand the null space in the image, then you should be able to tell me, what dimension it is, at least, what dimension it's sitting in, what vector space it's sitting in. Any questions on that idea? Okay.
So what does it mean exactly when suppose you have the image of a matrix and it's in a higher dimension? Does that make sense? Like we can look down on 2D, but we can't look up to 4D.
What do we can't look up to 4D?
Like we can't picture 4D.
Oh, I can.
Okay, well I can't.
Yeah. You ever watch someone move around?
Yeah.
You're looking at 4D. It's called time.
Okay.
You see? 5D is a lot harder, by the way. 4D, we're all good with 4D. You just never thought of it that way, probably, right?
No.
But time is a dimension. And by the way, this is going to get weird, but since I know you're a major, time isn't any different, really is hardly any different than X, Y, and Z, the spatial dimensions.
Interesting.
And you won't learn that for a while, but that's what Einstein figured out. And you trust me on that one. Sound good?
Sounds good.
I didn't come up with it. Einstein did. But Einstein's like my hero. So I definitely have read about Einstein in a big way. So 4D really is our universe. Okay, 5D is a lot harder. Okay, but the key is you don't have to draw. How many pictures do you see me drawing?
None.
None. Okay, you don't need pictures. Okay, some of the main applications of this is in like a million D, where nothing to do with spatial dimensions. It has to do with a million different variables that you're looking at to try and figure out artificial intelligence or whatever you're doing, or economics or something like that. Okay, does that make sense?
Yeah.
Right. Or if you're looking at the S&P 500, that's 500D. Right. So again, doesn't always have to be spatial. So these matrices don't necessarily represent forward, backward, left, right, that kind of stuff. So that's important to remember. Okay, so how do we find the null space, the nullity, and the image of this matrix here? In just a second. So the key is it's the same matrix that I had before. So what can we do?
RREF it.
Yeah, REF it, which I think we've already done up higher. So there's no reason to work on it again. So let's copy and paste. Okay, so we now know RFA, and I'm trusting you. I didn't do it, but hopefully you put it into a computer right and got it. But it looks right. I do know there's 2 rows of zeros because when I created it, I wanted to make sure of that. Okay, so now let's start with the null space. And that is equal to Let's write a basis for the null space. And what is that?
It's the set of vectors 1, 0, 4 and 0, 1, -9.
Does that work? It's really easy to check that. Well, first thing, what dimension is the null space in? It's R what?
M, so 3
M's not 3 here.
or 4.
4. So it can't be 1, 0, 4. Do you see that?
Yeah.
So first thing, it's R4. And you always want to keep that in mind so you don't make that mistake in getting the wrong dimension. Does that make sense? Okay, so that's not going to work. Instead, you got to really go back. You got to go back to the first day of class. What did we do the first day of class? And second day, first and second. Huh?
Matrix operations.
Matrix operations. Actually, that was the second and third day. This is what we did the first day. No one remembers. I know. It's been in 3 weeks already. Okay. We solved systems of equations. You remember with the matrix? Do you remember doing that?
Yeah.
Okay. And now we have a homogeneous system. What's the free variable?
3 and 4, rows 3 and 4.
There's only, yeah. So this one is R3, right? So it's going to be Z. If you think of it as X, Y, and Z, Z will be the free variable and X and Y won't be free. Any questions on that? So the null space, we only have one free variable. So it's a span of only one vector. And it's the span of the vector. I'm going to write as a row because it's easier. It's going to be the span of the vector -4, comma 9, comma 1. How did I get that vector?
Z equals -4 plus 9.
Z equals -4 plus 9.
Yeah, -4x plus 9y, maybe.
I'm not sure. Maybe I'm not following you, but just read the first row. This is x plus 4z is equal to 0. Or x equals -4z. Let z be 1. X is -4. Here we have y minus 9z equals 0, or y equals 9z. So y is 9. Is that clear? I'm a little worried about this because this isn't working. That's what happens when I trust you on the RREFing. Because if we multiply, let's see, -8. Oh no, it did work. Good. Sorry. I did arithmetic wrong. Yeah, this works. Okay. Any questions on how I got this? How do you check your work? How do you check to make sure you didn't blow it on the RREF, for example? Or anything else?
We can make sure to use the span to get the other vectors.
It's very different than that. You just take the dot product. So you multiply this original matrix by -491 as a column, which means take the dot product of each of the rows with -491, and you better get 0 for all of them. Does that make sense? And you do. What's the nullity? Easy. This is an easy question.
2.
No. It's easy. But it's only easy if you know what you're looking for.
Oh, 1.
It's 1 because it's a span of one vector. right? We found the basis. The basis has only one vector. Okay, how about the image? So how do we get the image?
We dot A with our vector we just found.
You dot A with the vector. No, it's a little easier than that. All you do is you say the pivots are the first two columns. Do you see? So you take the first two columns of the original. And that's going to be 2, 1, 3, 5. And 1, 0, 2, 2. Guess I should make it a set and make it a span. Any questions on the image? Okay. So there's our image of A. And that's it. All right. Now comes a big important theorem. This is used a lot. And we can see it works. And that is that if you look at your A and you take the rank of A, the rank is 2. Do you see that? The nullity is 1, and the rank plus the nullity is always the number of columns. And the reason why this is true is the rank is the number of pivots, the nullity is the number of free variables. And the number of pivots plus the number of free variables is always equal to the number of columns. Any questions on this theorem? We've really had this theorem before. We just didn't have the language to write it this way. But we've talked about it. Okay, let's move on. Okay, this is a TFAE, but not the TFAE. I want to note that. This is for an M by N matrix. And that is if the rank of A equals N. So that means if you take the number of columns, and that's your rank, then that's the same thing as the row space of A is all of Rn. And that's the same as the columns of A are linearly independent. And that's the same as A transpose times A is invertible. And that's the same as there exists a matrix C such that CA is the identity. By the way, if there exists a matrix C such that CA is the identity, does that mean A is invertible?
No,
Why not?
it's not a square matrix.
Right. If C is not, if we didn't start with a square matrix, then you can't say it's invertible. Okay, we had an M by N, and M are not necessarily equal. If they are equal, then it's invertible. But if they're not, then no, you can't say that. But you do know that a transpose A is invertible. Okay, which does not say that a transpose is invertible. Any questions on this? So I'll let you look at each of these, one at a time, a little more slowly. Okay. Note if the rank of A is N, that means there's N pivots, right? It means there's a pivot for every column. Is that clear? Well, if there's a pivot for every column, then that means that the columns must be linearly independent because the column space must be Rn. The row space must be Rn. Okay. A transpose A is invertible. That's a little more work. I don't have time to prove that today, but you could look at it in the book or whatever. Any questions on this theorem? Have you noticed we have a lot of definitions and theorems in this class? More than you've ever had in your lifetime? Sound right?
Oh yeah.
Yeah, that's his class. There's no hard math, but there's a lot of theorems and definitions, and that makes this class brutal. Even though mathematics is just arithmetic. Do you agree? It's all arithmetic. But this is definitely I think it's the hardest class in all of our math classes. I don't know if you agree, but most people think so. Okay, and number 6. I forgot to number 6. Sorry about that. That's what happens when we cross a page. There we go. The null space of A is trivial. So that means if you're looking for an x such that ax equals 0, then x equals 0 is your only solution. Any questions on that? Okay, and you know the null space must be trivial because you know that the nullity plus the rank must be equal to n. And if n is the rank, then that means the dimension of the null space is 0, and that means we have a trivial set. That's it. That's the proof there. Any questions on this? Okay, the next theorem is really the same theorem, except I'll let you take a look at it. What are we going to do to A first to go from the first theorem to the second theorem?
Sorry, I was confused too for a second, but I
Transpose.
Take the transpose. And notice that when you take a transpose, everything about rows becomes about columns. Everything about columns comes about rows. Is that clear? So m by n becomes n by m. It switches those. So the m's and the n's get switched. Do you see how that works? The word row becomes the word column. A transpose is A transpose. Because remember, you switch the order when you take transposes. Any questions on that? So CA becomes A C because you switch the order. So all this stuff works. Okay. Number 6 looks a little different, but if you think about it long enough, it's the same. So the second theorem is just the theorem for the transpose. Any questions on this? Okay, so now we're done with theorems, which means we're back to definitions. What does orthogonal mean geometrically, by the way?
It's in a direction of pi over 2 from something.
Good, good. Or it's perpendicular direction, pi over 2 angle, right? But that's really hard to do when you have a 100-dimensional thing. Do you agree? How do you measure an angle in 100 dimensions? If you have an idea, let me know. I'll be like impressed. And the answer is you can't visually, that's for sure. So we tend to not use the geometry word, which is perpendicular, by the way. Instead, we use the word orthogonal. And what you learned third quarter, we actually had the word orthogonal, but we didn't do it for 100-dimensional vectors or general vectors. But you actually got this, those of you who had me, you got this from me, even if you don't remember it, it's been a long time. And that is that if you have a bunch of vectors, v1, v2, ... vk, we say this is an orthogonal set of vectors if the dot product of any two vectors in this set, distinct vectors, is equal to 0. Or in other words, vi dot vj is equal to 0 for I not equal to j. Any questions on that so far? Okay, very important definition. And let's back up a bit. So I have some examples, and I want you to try it. This isn't a hard definition, so I'm hoping you can do it without me showing you. And that is, the first one is determine if 2, -1, 3, comma 4, 2, -2, comma 1, 1, 0, is that an orthogonal set? And the second is determine if 1, 0, -1, comma 1, √2, comma 1, comma 1, √2, comma 1, is that an orthogonal set? So I want you to work those out using this definition. The hint is this isn't supposed to be hard. You can use pencil and paper if you want. And I'll give you a minute or two and see how you do. Maybe I'll call them example 1 and 2 so you can refer to them. And put in the chat box what you think when you're done. Remember, put in the chat box, waiting for at least few of you to tell me. Maybe I'll even make it prettier and not get the warnings about grammar. There's no grammar issues here. That's better. And so far, no internet problems, which is good because it's snowing hard, at least at my house. I don't know about your houses. All right, so we got some different thoughts. And so let's look at them. Let's start with example 1. Okay, I'm just going to call it V1, V2, V3. How many do we need to check? We need to check V1 dot V2. What do you get when you dot V1 and V2?
0.
You get 0. Okay, does that mean that this set is orthogonal?
Yes.
One more guess.
No.
Not yet. No, it's not good enough to just check one of the pairs. You have to check all of the pairs. How about V1 dot V3?
No.
No.
You don't get 0.
No, I dot them. I get 2 times 1 plus -1 times 1 plus 3 times 0. And that's a 1. Do you agree?
Yeah.
So for example 1, V1 dot V3 is equal to 1. So this is not an orthogonal set. Any questions on that? Okay. Do I need to check V2 and V.V3? Do I need to check those?
No.
No. Once it's not orthogonal, you're done. Okay. How about example 2? What's V1 dot V2?
0.
Good. V1 dot V2 is 0. What's V1 dot V3?
Zero.
That's 0 also, right? And what's V2 dot V3?
Not 0.
All right, what is the square root of 2 times the square root of 2?
Oh, yes, it is 0.
Yeah, it's 1 minus 2 plus 1. And that's 0, by the way. Okay, and that's it. There are 3 different pairs of points to check. Okay, by the way, if there were 100, if it was an R100, if there are 100 vectors, how many checkpoints do you have to do? Any guess? So if there are 100 different vectors, how many checks do you have to do?
Well, 100 checks.
Actually, a lot more, 5,050. Because it turns out it's 100 choose 2. And if you work that out in your head like I did, you get 5,050. Got it? Do you believe me? So there's a lot of checks in large data sets. Okay, and it's of the order of the square of the number of vectors. It's not the square, but it's of the order of the square. So it's a lot of checking. Could take a computer a long time, for example. So this one is yes. So V1 dot V2 equals I hate that it makes it capital, equals V1 dot V3 equals V2 dot V3 equals 0. So this is an orthogonal set. Any questions on that? Any guess on why you use this, why you want orthogonal sets?
Because then maybe you can set up for yourself a definition each time. You know,
Your
v1 dot v2 is always 0.
Yeah, it makes life easier when you're doing calculations. Also, for example, if you're looking, let's say you're looking at the universe, okay? By the way, are there natural coordinates for the universe?
Probably like quasars.
No, there's no natural coordinate for the universe.
Oh.
Wait, where is the center of the universe?
Oh yeah, no, I don't know.
Okay, so that's the thing. By the way, you're at the center of the universe. Do you know that?
Our epicenter of the universe is the Earth, or at least
the
the visible universe.
And here's the thing, and just trust me on this one, and this comes from Big Bang Theory, is that every point is the center of the universe. And that's because every point was in the same place at the very beginning, as long as you go back in time long enough. So the point is, the problem is even if you choose yourself as the center of the universe, got it? All right, then you have to choose your X, Y, and Z axes. Is there a natural X, Y, and Z axes to choose?
No.
Not really. But what you want to do is you want to make sure they're orthogonal. Do you agree?
Yeah.
It makes life easier for doing all kinds of math if you have orthogonal coordinates. So the reason why we care, one of the main reasons why we care about being orthogonal is so that we can have a coordinate system. Because when you're talking about a basis is a coordinate system. And we're going to get into this later in this class. But a basis is a coordinate system for Rn. So you have to choose your coordinate system. And if you choose an orthogonal coordinate system, you've done a pretty good job. But you could do better. How could you make it even nicer than just requiring orthogonal?
Planar.
Well, planar doesn't help if you're in R3. Do you see? Because you need 3 dimensions. Okay, the idea is not only do you choose the direction of the vectors, but you got to choose the length of the vectors. Do you agree? To be your basis. So what's the best length to pick? What's the easiest to pick?
The unit vector, length 1.
1. So that's our next big definition. So our next definition is that V1 through VK is orthonormal. So it's an orthonormal set if it's orthogonal and VI dot VI is equal to 1, which is the same thing as we have a unit vector. That's what it means to say we have unit vectors. So then we have what's called an orthonormal set. So a lot of times what you want is an orthonormal basis, because if you have an orthonormal basis, it's often a lot easier to do the math when you're manipulating stuff. Okay, now there is one orthonormal basis you all know about in R3, and what is that? Identity. You're probably thinking the right thing, but those aren't the words we use.
The standard basis.
The standard basis, yeah. Yeah, you keep wanting to be identity, but it's called the standard basis. Identity is for matrix, but this is a set of vectors, which is a little different than a matrix. So the standard basis is definitely an orthonormal basis. I think you all agree that the dot products are all 0 if you take different ones. And if you take a bunch of zeros and a 1 and then a bunch of zeros and you dot with itself, you get 1. So that's definitely the example of an orthonormal. Are there other orthonormal bases?
Sure, why not?
Yeah, in fact, for R2, let me tell you, we got 2 minutes left, which is maybe enough. I might go 2 minutes extra though. For R2, because that's the one I have enough time for. They all look like the following. Maybe not X. Is theta quick and easy? There it is. So cosine theta, sine of theta, negative sine of theta, cosine theta. So it turns out if you look at the columns or the rows, it doesn't matter. They will be orthonormal. And that's the only ones. Every orthonormal collection of vectors in R2, collection of 2 vectors in R2 is of that form. So that you can look at as columns. I'm writing as a matrix so I can jump to the next step. Any questions on that?
Is it coincidence that the determinant of this matrix is 1?
No, not a coincidence at all, because a matrix is called orthogonal if the matrix, and we're going to use U now because this is very special to be orthogonal. So U are orthogonal. U transpose equals U transpose U equals 1. What that means is that U transpose is the inverse of U. Got it? Now, if you take the determinant of both sides, you get the determinant of U squared equals 1. So the determinant's either going to be 1 or negative 1. Okay, now just a note, and this is a pain in the butt, but orthogonal means that the columns are orthonormal. Unfortunately, we don't call it an orthonormal matrix, we call it an orthogonal matrix. even though it means that the columns are orthonormal. So what's good about an orthogonal matrix is that the inverse of an orthogonal matrix is very easy to find. You just take transpose. And I think hopefully you agree, taking a transpose is a lot easier than taking an inverse, especially by hand. Do y'all agree?
Yeah.
Yeah, there's no RRFing. You just switch the rows and columns, you're done. So if you have an orthogonal matrix, inverses are wonderful. Okay, any questions on this? Okay, we're out of time. So I'm not able to do this example, but I'll let you look at it and you can do it another time because we're out of time. So let me stop the share, stop the recording.